My name is Charles Zona, and I would like to welcome everyone to today's Macron Group webinar. Our presenter is Wayne Niemeyer of Macron Associates. Wayne is a senior research scientist with Macron Associates and has over 40 years of experience. Wayne is going to talk to us about the curse of the light microscope. Most of you probably know Wayne as an expert in electron microscopy. However, Wayne is an accomplished light microscopist as well and uses a wide variety of light microscopy techniques, including polarized light, fluorescence, and many other contrast methods. For Wayne, the curse of the light microscope began well before college. In fact, it started when he was 10 years old after receiving his first light microscope as a gift. Wayne is going to tell us what the curse of the light microscope is all about and then field questions from the audience. And this webinar is being recorded and will be available on the Macron Group website under the Webinars tab. And now I will hand the program over to Wayne.
Thank you, Chuck, and welcome everybody. I certainly appreciate all of you taking time out from your busy schedules to join us today. I'm going to talk to you about the curse of the light microscope. At least I call it a curse. And it's a good time to talk about curses. It's the month of October. We have Halloween coming up later at the end of the month. And tomorrow is Friday the 13th. And we know what that means. Okay, so Chuck mentioned that we had this curse for a long, long time. As he said, I've had it since I was 10 years old. And but the curse goes back way farther than that, actually. And if we can advance the slide. There we go. Okay. So now I can give you some historical development of the microscopes and where the curse actually began, I guess. Circa 1590, Hans and Zacharias Janssen combined two simple microscopes to form a compound microscope. Then, circa 1665, Robert Hooke devised a compound microscope to observe opaque objects. You'll recognize the name of Robert Hooke because our Hooke College of Applied Sciences is named after him in his honor. Circa 1681, Christian Huygens invented an ocular for the telescope, which was later adopted universally for the compound microscopes. Then around circa 1800, Thomas Young corrected lenses for astigmatism. Circa 1873, Ernst Abbe designed a chromatic substage condenser, which you'll find is furnished with many of today's microscopes. In 1886 or so, Abbe, Schoute, and Zeiss collaborated to perfect apochromatic lens, objective lenses. And then circa about 1900, around 120 some years ago, the compound microscope had essentially evolved into its present form. Now, as we all know, there's been lots of activity going on, microscope improvements, modularization of microscopes in today's world, and all kinds of accessories and filters and so on that come with them. If any of you get a chance to come to the Macron Group here in Westmont, Illinois, I really urge you to take some time out to visit our microscope museum. It's the Brooks collection of microscopes. Don Brooks is the owner, CEO, and chairman of the Macron Group. And he has, over the years, acquired so many of these antique microscopes. And a lot of them are on display now here. Approximately 200 are on display, and another 200 to 300 are in storage. The earliest microscope in his collection is circa 1680. The collection also includes about 2,500 volumes of books on microscopy and optics, dating all the way back to 1630. It's an incredible collection. It's an incredible site to spend through if you get some time to tour. On the right-hand side here, we have a couple of microscopes from his collection. One's from circa 1870, and the other one from the mid-1700s. These are fully functional microscopes still after several hundred years. You notice on the circa 1870 microscope, those of you that have compound microscopes, you'll probably recognize the substage condenser that's right below the stage and above the little mirror. That condenser still looks very similar on today's microscopes, over almost 200 years later. So what happens with this curse? It begins and intensifies as soon as you buy or inherit any microscope. That's why it started with me when I was 10 years old. It starts to intensify, though, as you start using that microscope to examine various objects. And then it intensifies even more as you learn about microscopy through your brute force experiences, reading various microscopy literatures, participate in formal training classes like they have here at the Hooke College, or attend microscopy conferences, seminars, and webinars like you're doing today. So what is this curse? Simple. It's lighting. Just lighting techniques to view objects under the microscope. Here's examples of a basic compound and stereo microscope, circa late 1980s when these first came out. These are the two microscopes that I inherited here at McCrone Associates when I started here in 1992. These are, just basic scopes, but as the curse starts to intensify, you want to add to it, and it's the lighting that you want to add. So here's what happened with the stereo microscope. We included some extra lighting. In the back left side is the stage, which has the transmitted light capability, which replaces the normal stage that's in the center. Then in the left-hand front, we have the ring light. And this ring light attaches to the base of the objective lens to provide nice circular lighting around the sample. We also have to have some sort of a module to attach a camera to it now. Then we have what's known as coaxial illumination, where two parallel light beams come down to the surface of the sample and reflect back up through the objective lens. You also need oblique lighting, and for that I like to use the black gooseneck halogen lamp in the back here, and that really floods the entire field of view with a nice bright light. The compound microscope is more complex, and this is only a selection of some of the accessories that you can get for the compound microscope that I had here. There's all kinds of filters, prisms to insert, different light sources to insert into the system, and certainly can do reflected light and transmitted light, that sort of thing. And you can use that gooseneck halogen light for some oblique lighting as well. So when we put all this stuff together on the circular table, that's the final setup, as I called fully equipped. It's not really fully equipped because there really are more accessories that you can even get for it. But this is the fully equipped system that I was using. And on the right-hand side, we have another compound microscope specifically set up for fluorescence microscopy work. That was done because the fluorescence light source is different than the standard light source, and you have to keep switching them back and forth on the compound microscope if you just have one. This way we had a second one that we could just dedicate to the fluorescence work. So I'm going to show you some examples of different lighting conditions taken from the stereo microscope. But first I want to give you what I consider minimum requirements for illumination systems for your stereo microscope. First of all, you need some oblique lighting capability. Then you need the reflected coaxial illumination. Then a ring light. And finally, transmitted bright field and dark field lighting. And I'll give you some examples of these various things. So here's a crater defect in paint. The crater is formed in paint when it's applied, and there's a contamination on the surface of the substrate where the paint is not compatible with that contamination, and it pulls back in a radial fashion from that contaminant and forms a nice circular ring with a ridge around the outer perimeter and a depression inside where the contaminant will reside. So with oblique illumination, in this case the oblique light is coming in from the right-hand side of the image, and we can see that the right-hand side of the crater is dark on the inside of the wall of the ring and shadowed, and then on the other side it's not shadowed anymore, so the inside wall is brighter. And inside we can see some sort of contrast shadowing effect. But it's not a really good way to look at the crater defect in paint. Now, if we use the ring light, we can see now that that crater is pretty much invisible. Can't really tell much of anything about it. And that's because the ring light is producing light source from a cone, if you will, all the way around the 360 degrees, so it's eliminating all the shadowing effects. So on flat surfaces like this, or surfaces that have very small topographical features, a ring light's not going to really help you very much. The coaxial illumination, though, is really fantastic for these smooth type surfaces. Here is the paint crater now. We can clearly see it in the center of the field of view here, and right in the center of that circular region is our little black contamination material. Now we can get in there as we're viewing it in the coaxial illumination, and we can isolate that contaminant particle and mount it for other analyses to find out what it is. Here's an example of what I called comet defects on polished brass. Now with oblique illumination, the polished brass doesn't look all that bright, and you can see bright speckles and lines and so forth from the various ridges in the topography of the brass. If we look at it with a ring light, now we can see a little more detail. And you can see the two bright spots to the upper right and lower left side of the image, and kind of a wispy tail coming down toward the bottom of the image from each of those spots. Still not real good detail, not a really good view of it. Let's go back to the coaxial illumination again. Now we can really see the fine details on the surface. And look at the difference in the roughness appearance compared to the oblique and ring light illumination. Coaxial illumination is just fantastic for what we would consider smooth samples. And dark materials like the red paint, even black, something black, it'll show up very nicely with the surface features. Here's an example of a deposit that we put onto polished beryllium plates. We typically use beryllium plates if we're going to do some work with the scanning electron microscope to get some elemental composition information from the materials. So on the left-hand side, we have what is known as just the regular coaxial illumination, and we can see the dark region within the deposit on the surface of the plate. But also with the coaxial illumination at the base of the objective lens, you would put on a compensator plate. It's called a quarter wave plate compensator that can be rotated. And as we rotate that compensator plate, the image goes from fairly bright, like it is on the left-hand side here, to get darker and darker. It almost acts like a polarizing filter that I'll discuss a little bit later. But as it gets darker to its darkest point, then you can start seeing a lot of different structure in the samples. Look at the beryllium plate now. Now we can see the different shades of blue which are outlining the grain structure of the beryllium metal itself, something that you don't see with the regular coaxial illumination. And this type of quarter wave plate extinction is really good for looking at polished metals and alloys to look at the grain structure of the metals. Now look at the deposit. Now we can see that that deposit has more of an orange color to it, but also notice that there's some bright white specks associated with that deposit. We couldn't see those bright specks in the coaxial illumination image, but now those bright spots are something else to work with in this deposit. And in the SEM, we can actually use this image as a map, if you will, to try to locate some of those particles to get their elemental composition, find out what they are. So let's get to the oblique illumination versus ring light. This is a burned circuit board, so it has a major topographical differences all across the surface. And in the left-hand image, we have the oblique light coming in from the left-hand side of the image. And we can see the shadowing effects. We can see in the lower left portion of the image that there's a very dark area that we can't really see very well. And certainly next to the three electronic component parts, behind them to the right is a very dark shadow. We can't really see anything in there. If we look at the ring light illumination, where now we're producing that cone of light 360 degrees all around the sample, we eliminate all the shadowing effects. Now we can start to see everything that's there and use the ring light on these types of features that have a lot of topography, very high and low features on these surfaces, eliminate all the shadowing effects, and now we can actually see what we're looking for and go in there to pick out materials if we need to for analysis. So I'll give you some examples now from the compound microscope. And again, I'll show you some what I consider minimum illumination systems for the compound microscope. Polarized light, very, very important. Transmitted and reflected polarized light. Reflected bright field and dark field imaging. Interference contrast imaging. And finally, the fluorescence imaging. So I'll go through some examples of these, and this is by far not a complete list of illumination or lighting systems for the compound microscope. There's many, many different accessories that can be put into place here to enhance or alter how you're looking at things with different lighting conditions based on the accessories that you have in there. So here's an example with the polarized light. The polarizing system has a polarizing filter in the base for the transmitted light, and that's a fixed filter. And as the plane polarized light comes through the sample in transmitted light up into the objective lens, then we have another filter above the objective lenses that is a rotating polarizing film. So now we can rotate the analyzer, as it's called, and cross the polarizers. And when we do that, we can now see various features. You can see in this image the foreign material that's embedded in that polyethylene film on the left-hand side. You really can't see much of anything in there. But with the cross polarizers, now we can see two very distinct features, these bright spots, if you will, that are emanating from something that's in the center of them. Those bright spots are formed from strained birefringence in the polyethylene film. And so it'll produce these strain patterns under cross-polarized light. So now we can go into the center of each of those little clusters and find the foreign material and extract it out of there for analysis to find out what it is. Here's another example of polarized light microscopy. If you're looking at samples that have a lot of clear crystalline materials in them, you can't really tell too much about them or try to differentiate them with normal plain polarized transmitted light. They're just clear fragments, and you really can't distinguish anything from one another if they happen to be different materials. One of the ways to help distinguish these types of things is to cross the polarizers again. If we do that, now we can see that some of these fragments have coloration to them. These are known as the birefringence colors, the retardation colors of the crystalline materials, due to different refractive indices based on the orientation of the crystals. So we can see in this image of the cross polarizers that now the glass background becomes dark, black, and it becomes black because glass itself is amorphous. It has no crystallinity to it. Therefore, it's not going to produce any of these colors. But also notice in the plain polarized transmitted light image toward the lower left side of the big fragment, there's another group of little fragments that are invisible now under cross polarizers. That's the material that is known as isotropic material. It does not have the birefringence as the other crystalline materials do, and we can easily differentiate now the isotropic materials from the more crystalline materials, or known as anisotropic materials in the samples. We can also show both of them at the same time. If we slightly uncross the polarizers, in other words, rotate that analyzer plate just a little bit more beyond full cross, we can start to see now some of the isotropic materials along with the crystalline materials, the birefringent materials. And then you can start sorting things out that way as well when you're trying to determine say, relative quantities of isotropic material versus the birefringent materials, things like that. Cross polarizers again. This is an example from electrolytic tin-plated steel. Electrolytic tin-plated steel is usually fairly shiny and bright and smooth, kind of a silvery looking appearance to it. And when we look at it with the polarized light microscope under the cross polarizers, this is reflected light now, cross polarizers, we can see coloration differences. These coloration differences are due to the crystal orientations of the tin in the tin-plated surface. So here in the center in the left-hand image, the tin crystal is a fairly large crystal, has a tan appearance versus the more bluish coloration of crystals around it. If we rotate the stage and 90 degrees, keep the polarizers crossed, and rotate the stage 90 degrees, now we see that the color shifts. Now the crystal is blue and the surrounding area is tan. This is actually a technique that's commonly referred to as optical staining. We know about staining various things with chemicals and so forth, but in this case we're certainly not using any chemicals. We're using optical properties of these crystals based on their orientation and what they look like under cross polarizers with the various colors based on their orientation. Here's some more examples of that. This is a painted aluminum panel. It's a polished cross-section, metallographically polished to a nice smooth finish, nice mirror finish. With regular reflected light, bright field imaging mode, we can see in the paint right in the middle, where the green arrow is pointing to, that there's a small crack or fissure leading all the way from the surface of the paint down to the base metal underneath. And that is a potential site for corrosion attack. Any liquid material that might be in contact with that paint surface can now migrate down through that crack and get to the aluminum underneath it and start corrosion mechanisms in place. So these are defects in paint that you definitely don't want to have. Now if we look at the same image in reflected light dark field mode, we can now see the crack a little bit better. It has a little more contrast to it. It's a little darker compared to the white paint matrix. But also notice how the aluminum surface now looks very dark, and we can see all the fine scratches compared to the nice reflected bright surface in the bright field image. For those of you that do metallography work and polish cross sections like this, and you look at your cross section visually and you look at it under the microscope with bright field type illumination, you think, oh, it's a beautifully smooth surface, mirror finish. Don't ever look at it with dark field then, because you're going to see all the little scratches and defects from your polishing compounds be highlighted very well. You can also use it, of course, as a quality control examination for your metallographic polishing. See how well you've really done. Now if we look at it with reflected light in cross polarizers, we can see the aluminum a little better now. It's the grayer area underneath. The white paint is still white and the crack is still visible, but not quite as visible as with the dark field imaging. If we look at it now with reflected light cross polarizers, and now let's insert into the light path above the objective lenses a filter known as a first order red plate. It's a retardation plate that retards light by neighborhood of 550 nanometers, I believe, something like that. And we have our rotating analyzer above that, leading toward the eyepieces. So with that first order red plate in place and rotating the analyzer, we can also produce different colors. In this case, the aluminum now looks blue, and the paint is still white, and we can see the crack still fairly easily. So again, this is an optical staining type technique with that rotating analyzer and the first order red plate. Here's an interesting example of various lighting conditions on some white particles that are dispersed. In this particular dispersion, they're on a smooth black carbon tape, and these are carbon tape tabs that we often use for the scanning electron microscopes to mount samples onto, just to adhere them in place. and used it that way. The black is from the carbon black that's put into the tape to make it conductive. Well, anyhow, in reflected light under the microscope, a lot of these particles look pretty dark. They're not white. They look very dark. And the reason for that is that these particles have tremendous topography variations. They're almost like crinkled raisins, if you will. So now the reflected light going into those particles is going to be reflected in all kinds of different directions, not always back to the objective. Certainly not 100% of that light's coming back to the objective and the eyepieces. So they're going to look dark. If we go to oblique lighting on the same tape, we can now see that the tape is black, like we would expect it to look, and the particles are mostly white, or at least whiter, but there's still some that are fairly dark, even under the oblique lighting. So let's go take that white powder and disperse it onto a glass microscope slide and look at it with transmitted light and see what we find. With the plain polarized transmitted light on the left here, now all these particles appear black against a nice white background or light gray background of the glass. That means these particles are very opaque. They might be white, but they're also very opaque. Not much light can get through them at all. That's why they look black. And you'll note that if these particles were dispersed in a much finer monolayer type dispersion, the contrast of black against the white background would be really good to do particle sizing measurements with offline particle sizing type software. So you can take a bunch of images like that and then collect the images into the software for the particle sizing. If we look at the particles, the same field of view with transmitted light, and cross the polarizers again, we see now that the glass has turned black, which it should, and the particles have a light gray color to them. Well, in polarized light microscopy with cross polarizers like this, we're actually looking at coloration due to birefringence of the materials, some crystallinity. In this case, these particles appear to have some very low level crystallinity. The coloration of a light gray is known as first order gray. As if the refractive indices in various orientations were more spread out, more different, the colors would start to go into yellows and reds and blues and so forth. But this is an indicator of a fairly low birefringence material, but it's really not the true color of the material. So if we look at it in transmitted light again, just with dark field, get the polarizers out of the way and look at it in standard dark field illumination, and we see that now the particles are white, and even the smaller ones now look quite light compared to the black background. And once again, these types of images with a nice monolayer thin dispersion can be used for particle sizing of these types of materials. Switching now to fluorescence lighting. This is an example of some general soil particles, looking at it with reflected light in the fluorescence mode. Fluorescence cubes are put into the microscope path, in the light path, before they go into the objectives to transmit only specific wavelengths of light from the electromagnetic spectrum. In this case, for fluorescence imaging, typically the wavelength of the light sources are going to be ultraviolet or violet, near ultraviolet, near violet type of wavelengths to impinge down onto the samples through the objective lens. Then the samples, typically in soil like this, minerals and various plant materials, have a natural fluorescence property where they will fluoresce the light back to the objective or to the eyepieces in the visible wavelength regions so that we can see the various colors. Now we can see that there's a lot of different shades of green and blue and aqua perhaps, and in the left-hand image there's a nice bright yellow-orange particle sticking out by us. Now I know from experience that calcite mineral, which is calcium carbonate, fluoresces an orange color under these conditions, so I suspect that that was a calcite mineral, although we didn't analyze it. On the right-hand side, right-hand image, we have a kind of a U-shaped object there that's a nice bright blue, and that's a synthetic fiber, and it's most likely mercerized cotton or linen to produce that type of a bright color under these conditions. And again, using these types of conditions, one can go in and select specific materials based on their fluorescent colors to sort them out and separate them for various analyses purposes. We can also use fluorescence microscopy for, let's say, man-made things. There are dyes known as chromophore dyes that can be added to resins, for example, in this case, that we can then use fluorescence microscopy for our examinations. In this particular case, it's an automotive paint problem where the paint was failing adhesion very severely, just sheets of the paint coming off. And this was being done when Ford Motor Company was first developing the painting systems for the thermoplastic olefin bumpers and fascia panels that are on cars today. They were having a terrible time with the paint adhering to the thermoplastic olefin. And we were able to help them out a little bit by making cross sections of some of these areas that had failed. And in polarized light microscopy, and I don't have a picture of that, but we could see that there was some crystalline material right at the surface of the plastic. And it turned out from some X-ray diffraction work that we did that crystalline material was recrystallized polypropylene from the thermoplastic olefin. And that forms during the molding operation. So the cure for that was to change the parameters in the molding operations to minimize and eliminate the formation of the polycrystalline polypropylene at the surface. So the dye, the chromophore dye, was added to the resin in the paint. In this particular paint, it's used as what they called an adhesion promoter, like a primer coat. And the purpose of it is to use the solvent carrier with the resin to penetrate down into the plastic surface to anchor it in place. If it can't penetrate into the plastic surface, then it's not anchored properly and it loses adhesion. So in this case, at the top image, we have no penetration. That would be very bad. So we were able to use the fluorescence microscope to look at cross sections of the samples that they submitted. And these cross sections were made by simple razor cuts, so there's nothing fancy about that. And just put it under the fluorescence microscope in reflectance mode and look at the colors. And at the bottom image, we can see what's known as the optimum penetration that they finally came up with. They did a study of bake and temperature time of the adhesion promoter on the plastic to determine the different depths that they were getting. And we could easily give them that information very quickly. And they finally decided that the 450 to 500 micrometer penetration depth was about optimized for their adhesion. And a lot of this information and work was published by Ford Motor Company. Dr. Rose Rintz, it's R-Y-N-T-Z. She published a lot of this in the journal from the Federation of Societies of Coatings Technology. It's their technical journal that they publish. So there's several articles that were published on this if you're interested. So let's go back to the plastic surfaces again. This is not paint, this is just a plastic surface. And let's look at the technique known as Nemarsky differential interference contrast, or NDIC as the acronym is used. In the left-hand image, we have standard reflected light in bright field mode, and we can see that there's some features on the plastic, but certainly with the NDIC capabilities, then we see much more detailed surface features that stand out quite easily compared to just regular reflected light. Again, producing an image or a view in the microscopes that one can go in there and start picking off or cutting out some of these materials for analyses. Some more NDIC. This is another polymer that had a lot of surface defects in place. In the regular reflected bright field mode, we couldn't see anything. But with NDIC, they're easily visible, and now again, they can be isolated and brought out. There's different types of things here. Right in the center of the field of view, we have an irregular shaped material embedded in there. There's some more off to the left-hand side of the image. And then we have a lot of these little circular knobs, if you will, that are probably a different material that can be cut out. NDIC again with a plastic surface where a paint was applied to it and failed miserably in little blotches. And we couldn't see anything on the surface of the plastic where it failed, and we couldn't see anything on the backside of the paint either under the microscopes. But with NDIC, we could see on the substrate that there was an oily film. Now in this specific image, you really wouldn't be able to tell if it's an oily film or a liquid film, or if it's just the surface flattening of the features on it just from some kind of physical mechanical force. But if you take a needle and while looking at this under the microscope and just put the needle into that region a little bit and move it a little bit, you can see that it's actually a liquid. So now we can go in there and we can extract that material and take it out for mounting for infrared analysis to find out what that oily film was. Here's some glass, NDIC. Under normal conditions, glass is very smooth, very little surface feature to it unless you have some dust on it, of course. But if you really clean it off well, the glass is usually very smooth, and even with NDIC, can't see very much features or topography. But if there's a physical defect embedded in the glass, NDIC is a really good way to see it. And in the bottom image, the area that's labeled as 1 is the foreign material that's embedded in the glass. It's kind of a yellowish color here. And the other objects or features that are identified in rectangle number 2 are actually refractive index variations within the glass due to the presence of the physical defect that's embedded in there with it. Okay, that's really the tip of the iceberg for imaging capabilities and illumination capabilities and so forth, but I hope that gave you some thoughts on how things can be done and how you can improve things and get different lighting conditions, because you never know what you're going to run into. And different lighting conditions can really reveal the true nature of the various things you're looking at. So for the microscopists out there that are really striving for perfection, this curse of lighting is absolutely unavoidable. And it's going to be costly. And you're going to have to initiate these budgeting battle plans really early to convince your management that this stuff is really going to be necessary. So I wish you good luck, and thank you for attending. Now we'll start taking questions. If you haven't already started typing them into the little box, the chat box at the lower right-hand portion of your screen, we'll start answering those. Can you explain how and why coaxial illumination creates such clear lighting when ring light does not? Okay, well, the coaxial illumination is actually projecting 2 parallel beams of light down through the objective lens to the sample, and then it's reflecting back up into the eyepieces. And that actually is a reflection technique where it's reflecting off of the surface in like a 2-dimensional plane, if you will, and it shows the surface as a reflection and kind of eliminates the color, I guess, if you will. It's more complex than that, of course, but that's kind of the simplified explanation for it. The ring light is producing like a cone of light. Think about the perimeter of a cone coming down to the focus point on your sample, and it's illuminating at that focus point all the way around the entire field of view. So it's really eliminating all the shadowing effects with the ring light. And that's what makes it more difficult to see features on smoother surfaces when you're using a ring light for your illumination compared to the coaxial illumination.
Okay, Mark, he's asking if you could please refer to the slide, the basic necessities. If you want to scroll all the way back there.
Yeah, I can get back to it. There it is.
Okay, those are the minimum requirements.
That's
right?
what I consider minimum requirements anyway.
Yeah.
Again, there's more that you can add to a stereo microscope, but these are the ones that I use quite a bit.
Okay.
Curtis, you said, can you please describe an examination scheme, say, for a visually smooth surface? What would be the sequence of lighting conditions for the exam? Would you use all lighting conditions for all sample types or certain ones for general categories of items? My typical answer to that is I'd use everything I have. But generally for a smooth surface, I would look first of all with the coaxial illumination. That really highlights the features on the surfaces with the stereo microscope. Now, if you need to go to higher magnifications, then you would have to go to the compound microscope and set it up for something like the Nomarski differential interference contrast illumination. Then you can see the fine detail on smooth surfaces. Let's see, Scott, is coaxial illumination significantly more expensive than ring lights or oblique lights? I would, I don't know, Chuck.
Well, I mean, you gotta buy the box, the light source for either one, and then it's a matter of plugging these things in.
I would think they're more expensive.
Yeah, and then the attachment itself, that intermediate piece is.
I think the best thing to do on something like that is to contact our Macron Microscopes and Accessories group here, and they can give you more information about pricing like that. Certainly, the oblique lighting. Like I have, just the gooseneck light is probably the cheapest, for sure.
Yeah.
And Shane, you say, why do we call things staining in light microscopy? As you said, it really isn't staining. Yeah, I called it optical staining. That's what we refer to it as over the years. And it's called staining like that. It's kind of in quotes because we're changing colors. We're manipulating colors based on how we rotate the filters in the microscope system. So it's a color change based on orientation of the crystals, orientation of the various filters that we're using in the light paths and so forth to change colors.
All right. Well, I think that might do it for the questions, Wayne.
Yeah, it looks like it.
Yeah. Thanks again, everyone, for attending.